Good morning, all. Today we discuss the formal solution of kinematical equations. Okay, if we know the acceleration, we can find the velocity and position using integration because we know that acceleration is equal to, in terms of velocity, we can write acceleration A is equal to dv divided by dt. And if we integrate the expression, we can obtain the expression for velocity, and we have a, a connection between velocity and position as v is equal to dr divided by dt. By using integration, we can find the position. Here, first we finding the velocity from the acceleration. If we know the acceleration, the velocity can be find out using integration. For that, we arrange the expression for acceleration as d of vt is equal to a of t dt. How it is obtained? Look at here. Here we write a is equal to dv by dt, and here a is a function of t and v also a function of t. Then we cross multiplying it. So we obtain dv, that is equal to a dt. Here it represents v is a function of t and a is a function of t also. Okay. Then if we integrate this equation both sides, we can obtain the velocity. For that, we assume we want to find v of t1. We have given the initial velocity v of t0 is known and the acceleration a of t also known. So We know the velocity at time t is equal to t0, and also we know that the acceleration. We have to find the velocity at any next time t1. So we take the integral on both sides of the above equation. Let us take here integral dv of t from t0 to t1, and here also we take the integral t0 to t1. I write here, first I integrate the left side of the equation. What will be the integral of dv? The integration variable is v, so we can consider that it is integral 1 dv. Okay, integral 1 dv gives the result v. V in the limit we will get v of t in the limit t0 to t1, that is equal to what? That is equal to integral t0 to t1 a of t dt, a of t dt. Here in the LHS we substitute the limits. We know that we have to substitute the upper limit first, then I write here it is v of t1 minus v of t0. We know that the first in limit is given minus the function with lower limit, v of t1 minus v of t0, that is equal to integral t0 to t1 a of t dt, a of t dt. Sometimes we need an expression for velocity at an arbitrary time t. Here we have got the expression of v of t1, that is equal to v of t0 plus integral t0 to t1 a of t dt. Here in this case, the initial time is t0 and we find the velocity at time t1. Now we want an expression for velocity at an arbitrary time t. Initial time, that is equal to t0. Okay. Then the only change will be here is to the limit of the integrations. For such a case, the integration limit can be different. That is, we integrate from t0 to t, t0 to t dv of t, that is equal to integral t0 to t a of t dt. Look at the equation carefully. Here the upper limit is t. Here the function depends on t. Here the function a depends on a is a function of t. And here the integral variable is also t. Then there must be some confusion. Here it is a limit. To distinguish the limit from the variable, we change the variable to a prime one. We change the variable to a prime. We change the variable t as t prime. It is not affect the result of the integration. Why? In the place of t dash, we substitute the limit, then the variable takes the limits. Okay. Then we will get the final result of this, as our aim is to find the value of velocity at an arbitrary time t. Then v of t must be equal to v0. v0, let it be the velocity at time t is equal to t0. Then v of t is equal to v0 plus integral t0 to t a of t dash dt dash. It is the expression for velocity at an arbitrary time t. Next we go to find the position. To find the position, we need the expression for velocity. We know that the velocity v of t is equal to dr divided by dt. Then we arrange it. Dr of t is equal to v of t dt. Suppose we want to r of t1 for a given initial velocity r of t0, and here it is not the acceleration. We Here we write the expression for velocity. So we know the velocity. Okay, velocity v of t. Then as we done in the previous, we have to take the integral on both sides from t0 to t1. Then the result r of t1 must be equal to r of t0 plus integral t0 to t1 v of t dt. Okay, here if you want an expression for position at an arbitrary time t, it can be expressed as r of t must be equal to r0 plus integral t0 to t v of t dash dt dash. As we mentioned in the previous integration, we change the t from t to t dash. It is known as t dash is known as dummy index. It is known as dummy index. Okay, it is a expression for position r of t is equal to r0 plus integral t0 to t v of t dash dt dash, where r0 is the position at t is equal to, here there is a mistake, it is not velocity, it is the position. Given initial position r of t0 and the velocity v of t. That is the former solutions of kinematical equation. Now we consider a special case of this, that is uniform acceleration. What does mean? It means that the acceleration must be a constant. Here we take the acceleration a is a constant and the initial time t0 equal to 0. Initial time t0 is equal to 0. Then we put these two conditions in our previous two expressions. We have two expressions, one for velocity and the other for position. That is, first expression, that is velocity v of t is equal to v0 plus integral t0 to t a of t dash dt dash. And the second equation, that is for position r of t, that is equal to r0 plus integral t0 to t v of t dash dt dash. Here in our case, in that special case, a is constant and t0 is equal to 0. Then we rewrite these two equations using the special condition. Okay, we have to find the velocity at time t, that is v of t is equal to v0. Here it changes, that is we know that a is constant. A not depend on time, then a can be take outside. Okay, this integration becomes this much. In the case of t0, in the position of t0 it is 0 and t then into a dt dash, isn't it? Okay, then it is v0 plus a into integral 0 to t dt dash. Then that must be equal to v0 plus the integral of dt dash. It must be equal to t dash in the limit 0 to t. Upper limit is t. Then only a into t. It is familiar to you. V of t is equal to v0 plus at. In the plus 2 classes, we did not v0 by u. Is it familiar to you? V is equal to u plus at, isn't it? Now we go to the second equation, that is r of t. I rewrite here, it is r of t is equal to r0 plus 0 to t v of t dash dt dash. In this special case, v of dt dash, v is equal to what? V is equal to v of t is equal to v0 plus at. Then in the place of v of t dash, v of t dash must be equal to v of t dash must be equal to, using this equation, v of t dash must be equal to v0 plus at dash. Substitute the value of v of t dash here. Okay, then r0 plus integral 0 to t, in the place of v of t dash I write in brackets v0 plus a t dash dt dash. Okay, then r0 plus integration v0 dt dash a t dash dt dash. v0 dt dash, when we integrating, v0 is a constant, then dt dash only the upper limit comes, then it is equal to v0 t plus a is constant, then it comes out of the integral, then t dash dt dash, it is t dash square by 2. When we applying limit, it is a into t square divided by 2. Okay, expression is r0 v0 t a t square by 2. Here the both are vector equation, so we can represent the velocity and similarly the position vectors, that is r r0 v0 and e. It is vector equations. For converting into one dimensional, for example, if we consider in the x direction, we will write the x of t must be equal to x0 plus v0 of x into t plus ax t square divided by 2. it is in x direction. In y of t is equal to y0 plus v0 y of v0 y into t plus ay t square by 2 in the similar way. Okay. Now we consider an example using the theories discussed. First, we consider the motion in uniform gravitational field, which means we know that the acceleration due to gravity, that acceleration is a constant. Suppose an object moves freely under the influence of gravity so that it has a constant downward acceleration g. Here we suppose that an object moves freely under the influence of gravity so that it has a constant downward acceleration g, small g. And here we choose the z axis vertically upward. So we have the acceleration. We have the acceleration that must be equal to acceleration in the direction of vertical direction. Okay, it is downward. Z axis is vertically upward. Then acceleration A must be equal to minus g k cap, isn't it? Minus g k cap. From this expression, A is equal to minus g k cap, you must understand that the acceleration is negative z direction, opposite to the z direction. Okay. If the object is released at t is equal to 0 with the initial velocity v0, here we consider the object is released at t is equal to 0 with initial velocity v0. We have to write the positions in the 3 dimension. For that, we write here the expression for position. General expression, that is r of t is equal to r0 plus r0 plus v0 of t plus half a t square. And we mentioned that when we express in three scalar equations, one dimensional equation, x of t is equal to x0 plus v0 xt plus half ax t square. We know that the acceleration only in z direction. So in x, the acceleration is 0, and in y also acceleration is 0. Only in the z direction acceleration is minus g, isn't it? Okay, then we can express. First we write the expression for x. X must be equal to x0 plus v0 x of t, and y is equal to y0 plus v0y into t, and finally the z is equal to z0 plus v0z into t minus half gt square. Okay, here we get three equation in the three dimension. One is for x, one is for y, and one is for z. Here the expression for z direction is different because of the acceleration is taking in the z axis. Okay, now for simplicity we can let the initial position of the particle is origin, or that is equal to 0. That means x0 is equal to 0, y0 is equal to 0, z0 is equal to 0. It is the origin. R0 is equal to 0 means it is the origin. The coordinate of the origin must be 0, 0, 0. So x0 is equal to 0, y0 is equal to 0, and z0 is equal to 0. And also we assume that v0y is equal to 0. That means the particle has no velocity, no initial velocity in the y direction. The particle has no initial velocity in the y direction. In the y direction, there is no velocity component. Okay. So the motion of the particle take place in which plane? There is no variation in the y direction. Initial y0 also is equal to 0, and v0 y is also is equal to 0. There is no initial velocity. So the particle does not go deflect towards the y direction. So the motion take place in xz plane. That it takes place in xz plane. Okay. So the previous equations, we have got three equations. First is x is equal to x0 plus v0 x into t, and y is equal to y0 plus v0 y into t, and z equal to z0 plus v0 zt minus half gt square. In that, the second equation vanishes because y0 is equal to 0 and v0y is equal to 0. And the first equation is simplified as x is equal to v0 xt because x0 is equal to 0, and z is equal to v0 zt minus half gt square. Okay, we get the x and z. The path of the object is shown in the figure. It is the path of the object. Is it familiar? The path looks like a parabola. This is the well-known parabola free fall projectile motion. Take it as homework that you have to show that the path or the trajectory is a parabola. Show it mathematically. A hint for the work is given. From the given two equations, we have given two equations. One is for x and other is for z. From these two equations, you have to show that the path of the particle is a parabola. For the hint is eliminate t from the two equations. Eliminate t from the equation and obtain an expression for z. The z must not contain t. Okay. Then you can show that it is a parabolic path. Next, we consider a non-uniform acceleration. The effect of radio wave on an ionospheric electron. We know that our atmosphere is classified into different regions. In that, some region is classified as ionosphere. Okay. Here we study the effect of radio wave and ionosphere. In the ionosphere, there may be electrons, free electrons. What do you mean by ionization? If an atom releases one of its outermost electron, then the atom is ionized or the electron is free. Here we take such a situation. Our problem is to find the motion of electron of charge minus E and mass M, which is initially at rest and which is suddenly subjected to an electric field. Electric field E0 is equal to E0 sin omega t. We know that an electromagnetic wave contains electric field and magnetic field. So we consider that case. Here we analyze the effect of electric field only. Okay, so our problem is finding the motion of electron of charge minus E and mass M, which is initially at rest, which is suddenly subjected to an electric field is equal to E0 sin omega t, where omega is the frequency of oscillation in the unit of radians per second. Here E0 is a constant vector and we shall choose our coordinate system so that x axis lies along it. Since there is no acceleration in y or z direction, we need consider only the x directional motion. Why we take there is no acceleration in y or z direction? It is clear from the Newton law. We know that F is equal to QE. Here we know that the charge of this electron is minus E, then F is equal to minus E into E. And using the Newton's law, we know that F is equal to ma. We equate that expression with this F. Then we get acceleration A is equal to minus E0 divided by M sin omega t. We take it as A0 sin omega t. Okay. So the electric field acting on the x axis. So there is no acceleration in y or z direction. Is it clear? Here the acceleration is expressed as acceleration a is equal to a0 sine omega t. a0 sine omega t. A is written as a0 sine omega t, where a0 is equal to what? a0 is equal to minus e0 divided by m. It is the value of a0. Look at here and compare it. Sin omega t here, sin omega t here, a0 in the place of a0 here minus e0 divided by m. Then a0 is equal to minus e0 divided by m. Okay. Then our aim is to find the velocity and position. We know that in the general case, v of t can be written as v of t is equal to v0 plus integral 0 to t a of t dash dt dash, that is equal to v0 plus integral 0 to t a0 sine omega t dash dt dash. Here I am not going to integrate this. You have to do. It is the other homework. Homework number 2. You should obtain the expression for velocity. You should find the expression for v of t. And next I go to find the position. We say that the motion take place in the x direction, then x of t is equal to x0 plus integral 0 to t b of t dash dt dash. So here in this v of t dash, it is the expression of velocity that you should have to find as homework. Then substitute the value of v of t with primed t here. Here we use t dash. That means it is dummy index. Then your next homework number 3, is to find the expression of x of t. Okay. Then for simplification, given that x0 and v0 is equal to 0. x0 is equal to 0 and v0 is equal to 0. So you have to simplify the expression for simplify v of t and x of t using the conditions above. It is the homework number 4. So in the last expression, you will get x of t must be equal to a0 into t divided by omega minus a0 divided by omega square sin omega t. That is, you will get the position as this one finally. Here the position containing two terms. The first term represent corresponding to the motion with uniform velocity. Okay, and the second equation, the second term is different. It contains a term sin omega t. So it is a different type of motion. That is, we know that the sine term that will varying one. So the second term corresponding to an oscillating term, then it give rise to a jiggling motion. So the electron have two types of motion. First is a motion with uniform velocity and the second is a jiggling motion. Okay. So I stop here. Thank you all.